Hi guys, this is demo for EE533 Lab 6. So I'll be going to give you a demo for the first part of the lab, which is extending the synchronous adder into ALU, which we will integrate into our pipeline data pack. So we made multiple primitives which were required and mentioned by the lab. So first we built a look ahead carry adder because ripple carry adder turns out to be super slow, especially with 64 bits. So we built a ripple carry adder. I'll show you the Verilog for the same. Sorry, we built a look ahead carry adder. Uh, this is the Verilog code for our look ahead carry adder. So we mostly use structural Verilog to save upon uh, gate and power. Similarly, we've uh, scrapped the old subtractor and we've used the same look ahead carry adder as a subtractor by uh, passing whose complement of v as an input. This is the Verilog code for it. We are just instantiating the LAC and passing the two's complement of v. And yeah, so the simulation works for everything. I can show you. And similarly, we built other logical components like comparator. Suppose a comparator, we've used the subtractor and we've uh, made a logic uh, that difference is zero, and without an overflow it is we raise the equal to signal in a one hot state encoded method, and if it's if a is greater than b, uh, we know that the difference is positive. So again, so we used 3 bits out of the 64 bit output as a one hot state method to say whether it's equal to or greater or less than. So I'll be showing you simulation for this. For the adder first. We go. This is the simulation for the adder. We pass the values using uh, a Verilog test bench. If you want to see the test bench, you can see this here. This is the test bench. So we made a few logical blocks, including logical shift. Uh, yeah, so logical shift. We made a muck, comparators, bitwise and, bitwise or, bitwise XOR, subtractor, and an adder. So the ALU is pretty much similar to what we did in our first lab, except that this is a synchronous ALU, which stores value on a positive edge of a clock. So this is our top module of ALU, where we can see all the instantiations. I'll proceed to simulate this. Yeah, so also in report it was mentioned to mention a table about which inputs do which operations. So it's pretty evident from the mux inputs that we are giving on which operations it does. For example, input 000 should do a sum, and we've left the a operation empty because it was not mentioned on what to do. So we will add it as per our own needs while integrating it into our pipeline next lab. And so if it's 001, we do a subtraction, and yeah, I'll simulate this. And then my uh, partner can continue giving them on the later parts of the lab. Yep. So this is the simulation for our synchronous view that shows the value on a positive edge of the clock. This. So we see select line 00 mean that we are adding numbers A and B. A is these at last, and 4 at again uh, LSBs, and the output should be 1, which is correct. And this only changes when there's a positive edge clock. So let me give you an example of that. So here you see the values are changed, but the output isn't changed. But once the clock is triggered here, the output will be changed. So A and B adds up to 5. Similarly, we have it for subtraction. So all the outputs are verified, working bitwise. Uh, yep. So this is the demo video for the components of ALU, and my lab partner would be continuing with the later parts of the lab.